Hi guys, something tells me it's time for a math video. I've heard some um, good comments about sometimes when I do math, and plus I said I would, and I said engineering, but same idea, and I haven't yet since I said that. So let's do it. Oh shoot, this new device here that helps me film better. Okay, so I'm gonna do an engineering video slash math. Ba- to me, basically, math engineering is just math applied to industry. You know how you make money out of math, because you can do two things with math. It seems you can build things and make money, in that, or do something with it practically, or you can teach it. But it's still basically the same type of thing. And I chose engineering rather than just pure math because I didn't want to just be up there teaching. I actually wanted to do something with it. But anyway, and I said something about De Moivre's theorem, and that's a tough one. But I said it so, sometimes the corniest things are actually hard to do. Like everybody thinks math is this nerdy thing, and isn't that stupid? But try doing it. It can be really tough, actually, even though it's like a geeky little thing sometimes. Okay, so I don't want to go over people's heads though. It's not, but I want to make it reasonable, and so you can follow my work. If you don't, you're free to check it with the professor. If you don't, they think you don't know what's going on. You can always say, "This guy for real," or what? I don't know. I'm trying to get good lighting in here. Sorry for the time here. Okay, enough of that. You guys can see it, I hope. Okay, a lot of the math a lot of the engineering I did was higher math because it used complex numbers and variables. Variables is the number that can vary. A complex number is a number it's a sum of a real number and an imaginary number. So it's really so you have to plot it on two dimensions. You have to plot it on a plane, where the x coordinate is real. That would be x. That looks like a plus. Let me get my eraser here. X is the real axis, which is the horizontal axis, and then the vertical axis is I, Y. So that's it's a multiple or whatever of I, so it's imaginary, and then if you take a point on it, it's the sum of the two coordinates, and that makes a complex number. So right here it would be like whatever, -1 plus I, maybe, so that Z would be -1 plus I, which is a complex number because it's got a real part and an imaginary part. Okay, but I've shown that already on my videos. And then what I've also shown, I'm just reviewing in case maybe this is the first one you've seen, or maybe you don't remember, or I don't remember, I don't know. And I said one of the best formulas for this is Euler's formula. Wait, this is going to be a tougher one because I'm going to apply some of this, I think. Okay. Euler's formula states that e to the I theta equals cosine theta plus I sine theta. You see that? Theta is an angle measured in radians, like I've said before, and it's measured so that in radians, you start on the x-axis and go counterclockwise for positive angles. That's just how it works. So an angle of 0 would be just the x-axis. And this is the complex plane, so it's x, okay? And then if you go, and then this angle here, which we normally call 45 degrees, would be 1/4 of a circle. But since a circle is 2 pi times the radius of the circle, then a full 360 cycle is 2 pi, because the circumference equals 2 pi r. So therefore, a complete circle is 2 pi radians, because if the radius is 1, circumference is 2 pi, and that would make so if 90 degrees, if 360 degrees is 2 pi, then 180 degrees is pi, and 90 degrees is pi over 2. So an angle of 90 degrees would be pi. That's theta, not pi. This angle would be pi over 2 for 90 degrees, for instance. Okay. Now so that we can erase that now because I just want to explain the angle part so you know what I'm saying when I say theta, because that's important. If you think theta, what was he talking about? Well, that's what it's an angle measured in radians on the complex plane in this case, because it's Otis theorem and that has complex numbers because there's a real number and an imaginary one. The sum of real number and imaginary number. Okay. Now, this is De Morbius theorem. I forget how to spell it. I could be wrong here. Morbius. Something like that. I don't know. Theorem. Or can I even spell theorem? Let's see. Theorem. Okay. Now it's really easy to derive, but I want to prove it by example. I want to show that there's an example I have that shows that it actually works, and then you can see a feeling for how it is, because you'll see an example of it if I show it to you, right? Okay. N is often a number, especially an integer, like 0, 1, 2, 3, 4, or negative 1, 2, 3, numbers that are whole numbers. So the Morris theorem says if you take E, I'm going to derive the Morris theorem here. Rather than just state it, I'm going to derive it. Okay, so E to the I theta, and then I'm going to say to the n power. So take this to the nth power, okay? So it's a complex number because E to I theta is a complex number because it's got a real part, which is cosine theta, and an imaginary part, which is I sine theta. But I'm going to take to the nth power so complex number to an nth power. That's interesting. Equals, it would be then the whole thing. Cosine theta plus, let's see if I can get this right, plus I sine theta, and then the whole thing to the n. I'm just taking the nth power of both sides. That looks right. Okay, fair enough. I'm deriving this as I go, I guess, because it's been a while since I've done this. But I know it works because I know it's a true theorem. True theorem. Truth. Okay. All right, there we go. Let me think. How do I do that? Let me think. Oh, I can do this. Okay, understand. Okay, I'm gonna erase this up here and continue writing from the top. I almost for a while there I thought, what am I even doing? But now I know what I'm doing now, and plus I know the theorem's right because that I already know. It's just a matter of can I derive it. Now in math, if you have a number, or this is a number to a power, and then the whole thing to a power, so for some reason you multiply these two. You take the original number and you take these two and multiply them, and that's what you get. In other words, E to the I theta to the n happens to be equal to E to the I theta times n. Okay, you just take these but let's show that, because anybody could say, well, is that even true? And if not, prove it. So let's just see if that's true with a simple real number thing. Okay, let's say I have 2 squared. God, I can't write sometimes. 2 squared to the second power. So all 2's. So this instead of E, I'm putting 2. Instead of I pi, I'm putting 2, and instead of n, I'm putting 2. Okay, see if and that, according to my theory, that would be equal to 2 to the 2 times 2. See, because he took the 2 and then multiplied the 2 times the 2 and put the original number to that power. The question mark. If you don't know if it's true, you put a question mark on top. Okay, let's see if that's true. 2 squared is 4, and 4 squared equals 16. Let's see if that's true here. Well, 2 to the 2 times 2, which is 2 times 2 is 4. The 2 to the 4th power equals 2 times 2 times 2 times 2. Let's see if 2 times 2 is 4. That 2 times 2 is 4. So 4 times 4 is 16. So sure enough, I showed that little trick works in a real number case. But if it works in real numbers, I'm just trust me, it works in complex numbers too. And you guys wanted to. I mean, I've told you good things about these videos, and I said I would do the Morris theorem, and that's what I'm doing. Okay, so if I have this, e to the I theta to the n equals e to the I in theta, then basically what I have is, this is really cool here. Watch this. E to the I theta to the n equals, now I'm going to write e to the I theta, but instead of writing theta, I'm going to write theta n. And that still will work. So if e to the I theta n, according to all this formula, e to the I theta n is just cosine theta n plus I sine, sine theta, no, put it on top, it's on theta n. Oh, there we go. Okay, let me put it in parentheses so you can see what's going on. If this now becomes, just put theta n in place of theta, so that would mean e to the I theta n is cosine theta n plus I sine theta n. And I said that was e to the I theta to the n. This is de Moivre's theorem right here. That's basically it. I mean, that's how easy it was to derive, but somebody had to do it and give their name to it. So it's called de Moivre's theorem, that a complex number to a power is equal to cosine of theta, e to the I theta to a power is equal to cosine theta n plus I sine theta n. And so that the theta n comes down here and then gets inserted into these, and that's de Moivre's theorem. Let's look at it a second. So if an imaginary power to let's say an imaginary number squared is just cosine of twice the angle plus I times sine of twice the angle. And let's test that, and then I'll be done. Okay, I'm gonna test that, and we'll be done. So let's erase this up here. Maybe let's erase the whole thing and restate it, and then I'm going to show you an example of it. I know that math is like, anyway, I don't know. Okay, so de Moivre's theorem says e to the I theta to the n equals cosine theta n plus I sine theta n. Okay, fair enough. That looks like O, but it's actually theta, and that's a sloppy one here. I want to take it as long as I can. I don't want to take longer than I have to. Okay, that's de Moivre's theorem. Now I'm going to test it for one case, and if I prove that, I'm going to let it go. Okay, I'm going to say if I prove it for one special case, I'm going to say we did it and I proved it. At least I did prove it, but let's show it by example. I mean, let's see if it even works. Okay, this is the complex plane again. Now what I'm going to do is, that's just an arrow. I'm going to take this, since I started with pi over 2 before, which is a 90-degree angle, I'm going to use that. So if the radius is 1, then this point is I. And this point back here, if this is 1, is -1, and this point here is 1, and this point is -I. So there's 4. I'm going to use those kind of things. Square pi over 2. So e to the I 0 is 1. E to the I pi over 2 is I. E to the I pi is -1. E to the I 3 pi over 2 is minus I. And e to the 2 pi is 1, like it's just like e to the 0 is, because a 2 pi angle is the same as a 0 angle. Let's see if it works for I times I. Let's see if that works. So first of all, what we should get, we know that this angle is pi over 2, and that e to the I pi over 2 is I. Let's write that out. E to the I pi over 2 equals I, because that's e to the I theta, which theta is pi over 2, equals I, and pi over 2 is a 90-degree angle. So, and then what I'm going to say is, does this work? E to the I pi over 2 equals I. Well, e to the I pi, let's make n squared. Let's square e to the I pi over 2 and see what happens. Okay, if on the left side, e to the I pi over 2, and then I'm going to square the whole thing, right? If I square it, I take the pi over 2 and I and multiply it by the 2, like I said before. So that would be equals e to the I pi over 2 times 2. That little x, yeah, well, I'm going to put an x for the time. So e to the I, pi over 2 times 2. But what's that? What's pi over 2 times 2? Pi over 2 times 2 is pi. So that would be equal e to the I pi. And what's e to the I pi? Well, if e to the I pi, according to this right here, it is minus 1, because if angle is pi, that's 180 degrees. So if I go pi, 180 degrees makes it negative 1. So e to the I pi equals negative 1. We know that graphically, but let's see if it works with this De Moivre's theorem. E to the I pi over 2 squared, that's what I had started with, e to the I pi over 2 squared, we now see is negative 1. Then the question is, I can erase the graph now because you guys get it. Almost done. Yay. I hate taking, time is important. So e to the I pi is negative 1. And we said that e to the I pi over 2 squared, which is e to the I pi, is negative 1. But then the question is cosine, theta was pi over 2, times 2, in was 2, so times 2, plus I sine of pi. Theta was pi over 2 and in was 2, so pi over 2 times 2 is, let's write it out, pi over 2 times 2. Okay, so is cosine pi over 2 times 2 plus I sine pi over 2 times 2 equal to e to the I pi, e to the I pi over 2 squared. Well, let's see. We said before that since e to the I pi over 2 squared is e to the I pi over 2 times 2, and pi over 2 times 2 is pi, that's just e to the I pi, which we know is negative 1. So the question is cosine pi over 2 plus 2 plus I sine pi over 2 plus 2 equal to negative 1 or not? And if it is, we've done our homework and we're done. So let's just see if that's true. Let's see if that's true. If I want to do that, I'm going to draw a little graph up here because I don't want to erase that one. It's too complicated to erase and expect to remember it. Is this true? Is cosine pi over 2 times 2 plus I sine pi over 2 times 2 equal to negative 1? Well, here's a little graph up here. You guys just mentioned it's bigger. It's a little guy. Cosine, so pi over 2 is 9 degrees. That's this guy. 9 degrees times 2 would make this angle, cosine, would make that equal to pi. So I would have cosine pi. All right, because that's pi over 2 times 2. And then plus I sine pi over 2 times 2, and that would be I sine pi. It looks like an H. That's a sine. Okay. So the question is cosine pi plus I sine pi equal to negative 1? Well, here's our diagram. Cosine pi, that would be pi is 180 degrees, so we're here. Cosine pi is negative 1. Sine, so that's this part, negative 1, plus I times sine of pi, but sine of pi is 0. So that's I times 0. And 1 plus I times 0 is 1 plus 0, which is, negative 1 plus I times 0 is equal to negative 1 plus 0, which is equal to negative 1. So there we have it. That proves a special case of if theta is pi over 2 and n is equal to 2, that e to the I theta to the n, which is in this is equal to cosine theta n plus I sine theta n, because e to the I pi over, in an example, e to the I pi over 2 total squared equals cosine pi over 2 times 2 plus I sine pi over 2 times 2. Therefore, e to the I pi over 2 squared then becomes e to the I pi over 2 times 2, which is equal to e to the I pi. So that's this, and that's equal to cosine pi over 2 times 2 because that plus I sine pi over 2 times 2 because pi over 2 times 2 is pi, and therefore that means that e to the I e to the I pi equals cosine pi plus I sine pi, and that works because that's always formula for theta equals pi, because e to the I pi equals cosine pi plus I sine pi, not theta, pi, pi, now it's blurry. E to the I, now that's not a pi, and that's not a sine, that's not a sine. Geez, I'm getting tired, I guess. Sine pi. Okay, e to the I pi equals cosine pi plus I sine pi, and that if pi and that is true because e to the I pi is this, and then cosine pi is -1, sine pi is 0, so e to the I pi equals -1. And so that's an example of a shows that De Moivre's theorem is true. Basically, all you're saying, let's just put it in simpler terms. When you here's a if you say e to the I pi over 2 squared, you're really kind of saying it's also can be thought of as e to the I pi over 2 is actually I. See that? Because e to the I pi over 2 is I, and then if you square it, what's I squared? Well, I equals the square root of -1. So I squared is the square root of -1 times the square root of -1, which equals -1. And that's true because e to the I pi is -1. And it all works. See that? You just took the I squared is equal to -1, but also cosine pi plus I sine pi is also -1. And that works. So what I proved is that if you want to square a number like I, you just double the angle. And if you double the angle, you get -1, but that's true because I squared equals -1 by definition. Even that's how I is defined, because I equals the square root of -1. So that may look like a bunch of nerd work and not even fun, but I bet a lot of people that would have a hard time doing that little lecture I just did. But that's not the point. I'm saying hopefully you guys learned something, enjoyed it. And one last little thing, I think I want to be redundant here because it's cool, but I don't have to. I could just quit the video right now, but then you'd be thinking, well, all I did is derive De Moivre's theorem. But don't forget this fun little fact: if e to the I pi equals -1, that in one step, basically, you get Euler's identity, because e to the I pi plus 1 equals -1 plus 1, because you're just adding 1 to both sides. And then I get e to the I pi plus 1 equals 0, because -1 plus 1 equals 0. And this is Euler's identity. It's got e, I, and pi. E is a transcendental irrational number that's equal to approximately 2.718281828. I is the square root of -1. Pi is a transcendental irrational constant approximately equal to 3.1415925. Those are three most important non-integer numbers in math. Then you have 0 and 1, which are probably the two most important integers in math. And you have plus, multiplication, and exponentiation, which are all the three operations in math. And an equal sign makes it an equation. One of the most beautiful, if not the most beautiful, formulas in math. In fact, it was mentioned on the show, Rizzoli and Isles, Sasha Isles. I think that's her name. No, maybe not Sasha. Whatever her name was, Isles is the smart one. And then there's always the tough one. The Isles. What was her name? Not Sasha. Anyway, the medical examiner for Rizzoli and Isles mentions this number. He goes like I like Euler's Euler's complex number E, and she mentioned something about it, which actually put that formula in TV. And the second time that happened, A Person of Interest, with Jim Caviezel and what's his name? Jim Caviezel and his partner, the nerd guy, what's his name in real life? I can't think of it, but he plays the nerd. What would that be? What was his character? He mentions anyway the nerd in what's his name? He played Ben in Lost. Michael. What's Michael? Ever something. Michael Ever. Anyway, something Michael Evers. Michael. Anyway, he mentions this formula in that show. Emerson, Michael Emerson. See, that's my photographic memory, but it was barely recorded in there. Michael Emerson. Yes, he plays the nerd in Person of Interest. Finch, Harold Finch. Okay, see that I remember that one now. He mentions this. There's identity in one of the episodes of Person of Interest, and he says it's one of the most beautiful. It's like he calls it a sonnet of math and beautiful, and he mentions it, and that's very cool. Love you guys. Peace. Rock and roll. Hope you enjoyed the lecture.